Good morning. Today I'm going to teach a new topic. It's on analysis and design of beams, shaft under combined loading. But first of all, we're going to do a revision on shear force and bending moment diagram. Okay, so for today, I will work on this example and also give a highlight of important points or summary of the theory on shear force and bending moment diagram. So in this example, you can see an overhanging beam. Support is at point B and point C, and between point B and point C, there's a evenly distributed load omega Newton per meter, and at the ends you have loads of P. So before we do anything, I want you all to start knowing about boundary condition. So we draw our transformation. So this is our X, and this is our Y, and then we start with our boundary condition, and we're going to call at the position X is equal to A. This is X is equal to L minus A. And for shear force and bending moment diagram, your datum is always on the left hand side. Okay, so your geometric datum is fixed. Okay, it's not going to move, and it's always going to be on the left hand side. Okay, so on left hand side. So in terms of boundary condition, I want you to start remember this sequence of flow. You have V, M, theta, Y, and your right hand side is also V, M, theta, Y, and V correspond to shear force, M bending moment, theta is the slope of deflection, angle of deflection, okay, and Y is Y displacement. Okay, due to deflection. Okay, so for this case, if you look at this beam, we don't know what's the shear at point A. At point B, where X equal to A. We don't know what is a shear force. We don't know what's a bending moment. We don't know what's a slope, angle of deflection. Okay, or we call it slope. Okay, but we know that Y is equal to 0. Okay, because you don't allow displacement in the Y direction. Likewise, at point C, Y is also equal to 0. So for this case, we know that this terms over here is known as our boundary condition. And I hope you will remember this sequence V, M, theta, Y. Is because later on we realize that when you integrate your shear force, you get bending moment, and when you integrate and then when your bending moment is equal to the elastic curve, we apply the elastic curve technique. You integrate, you get your slope, and then your deflection. Okay, so start remembering V, M, theta, Y. So first we carry out a static analysis. Here we carry out static analysis. So we know based on, okay, so before we do static analysis, we consider a free body diagram. We consider a free body diagram. So we follow the transformation we have earlier. So this is point A. This is our point B. So we know over here, that's our point D. So we are aware that you have P over here, Then you have P over here. This is your BY. And over here, this is your CY. And you have one equivalent load, right? And the equivalent load is equal to omega L minus 2A. Okay. So why L minus 2A is because the distance from here to here, right, this distance over here is L minus 2A. Okay. So from here, we know if we draw a line from the center, okay, we draw a line, okay, bad line. If we draw a line from the center, and we call the YY axis, you realize that YY axis is symmetry, loading, and geometry between the left and right. So based on symmetric loading and geometry, okay, about line YY, right, we can declare, okay, when symmetry, therefore BY is equal to CY. Okay, so on this stage, we do static analysis. I mentioned about forces, and the Y is equal to 0. So you have minus 2P minus omega L minus 2A plus twice BY, okay, is equal to 0. Then we know that BY is equal to CY is equal to P plus by omega over 2 L minus 2A. Okay. Then from here, so this is one equation, and from here, excuse me, we're going to form our shear force and bending moment equation. Okay. So if we just consider point A, okay, so this is point A. So point A where x is equal to 0, right? So it's just a very thin strip, right? And then we know that we have a P coming down, right? And then we have our shear force, right? So our shear force is, so this is equal to V at x equal to 0, sorry, x equal to 0, and then moment is equal to 0. Okay, so you write this out. Positive is going up. Summation about forces in the y direction is equal to 0. So what we have is P minus P minus V when x equal to 0 is equal to 0. V at x equal to 0 is equal to minus P. Then we take moment, and anywhere x equal to 0, so this will be equal to m, anti-clockwise m, 0, okay, is equal to 0. Okay, there's no perpendicular distance. Now let's look at point A. Okay, so this is done. Okay, so this is at A. Then we consider at point A. I'll do the next page. So if we look at point A, between point A to point B, right? 0, x to A. So now this is our beam. Datum is still on the left hand side. We have our loads. So our load over here is P. And then on the other side, okay, so V. So now this is in terms of X. And then our moment X down here. And then our slider is from left to right. So this is our X. So the question is, why the shear force and then bending moment are in this direction? So I'm going to do some side work to explain why. Okay, so I'm going to split this into two. One. Okay. So let's do. So when we deal with this, right, we call it positive shear and positive moment assumption. So let's review positive shear and positive bending moment assumption. Okay, so let's consider left to right analysis. And then we, on the other side, we do right to left analysis. Okay, so if we look at left to right analysis, okay, which is what is commonly done, I think you guys are very familiar with it on 2P. So left to right, this is your structure now. Okay, this is your geometric datum. Geometric datum is here on the left hand side. And then we have our slider X. And because you analyze from left to right, your shear force is coming down. And then your moment is going this way. Okay, so when you do right to left analysis, your geometric datum is still the same position, did not change. Now your beam, you analyze from right to left. Okay, so when there's a case, your slider, you will have to look at your slider. Your slider now over here is X, and the distance from here to here is L minus X. And when there's a case, this is your positive shear, and this is your positive bending moment. Okay, so this direction is what we call positive shear, positive bending moment, and hence you have this relationship. So from here, you do positive is going up, summation forces in the y direction is equal to 0. So minus P minus V as a function of X is equal to 0. So when there's a case, V as a function of X is equal to minus P. Okay, So this is your shear force distribution from 0 to A, and then summation about moment in the z direction anywhere at point x is equal to 0. So what does this mean is we are taking our moment at the red dot. Okay, so moment taken from here. Okay, so when that's the case, anti-clockwise positive, so you have minus px. Sorry, anti-clockwise positive, so px plus by m as a function of x. The whole thing is 0, so m as a function of x, so this will be equal to minus px. Okay, so now what does this actually means? Okay, what does this actually means? So in terms of shear force and bending moment, so we're going to construct, okay, I'm going to construct the shear force diagram over here. Okay, so our shear force diagram, so this is our shear force, and then this is our axis in x. Okay, so this is our x, this is our v, this is our 0, this is our a, over here is L minus A, and then over here is L. Okay, so we form a limit. Okay, we form a limit where we know that 0 to A, or at 0 we have minus P. Okay, so we have minus P. Then the diagrams goes from here to here, 0 to A, we know it's constant, so we have a minus P value. So that is for our shear force. So what you realize that our shear force, okay, from 0 to A is negative in magnitude. Okay, so next I'm going to construct our bending moment diagram. So this is our bending moment diagram. Okay, so likewise I'm going to label, so this is moment, so this is 0, okay, this is A, this is L minus A, and this is my L. Okay, so what we see now, our equation is equal to minus px. Okay, so minus px means it will have what? Negative shear. It's a straight line. Okay, so a very interesting feature to look at, okay, is you have over here, you have negative magnitude, and then over here you have negative slope. So from here we know the magnitude, okay, we have a relationship. So first thing to take note, the magnitude of the shear force okay, is equivalent to the slope of the bending moment. Okay, I'm going to stop here. I'll come back again to finish off the problem.